Yeah, so folks, yeah, I was talking to a muted phone. I am just going to start again. Give me a second. Hi, so can you hear me now? I have unmuted myself. Apologies. Yeah, so folks, yeah, it looks like this is fine. Let me just start again. Yeah, so folks, apologies for the little hiccup. I was talking to what is a muted muted setup. So I'm just going to start all over again. So today's lecture is about understanding computer vision, and we will. Okay, the agenda for today is it's about we've got to first talk about CloudxLab. We will then talk about the speakers. That's not only speakers, but there are a few other people who have contributed to this lecture, and we will talk about them, their backgrounds. We will then have we'll talk about to give you I'll give you an introduction on machine learning. I'll give you an introduction to very important concepts of machine learning, that's gradient descent and backpropagation. We will talk about deep learning. We will talk about how what are called CNNs, which are convolutional neural networks, and how they have contributed to computer vision. So we give you a background on machine learning and uh, deep learning, CNNs, etc. But the reason we're talking about is we try to focus on how it contributes and how it makes computer vision better. At the end of the day, what we'll do is I will demonstrate a hands-on with Yolov4 and OpenCV, and give you a hands-on, show you how it works, and kind of take you through it. We will do is we will yeah, so again, as I said, in case of your questions, in case you have issues just or questions, please write them on chat. I will follow them. There's a slight delay between what I see and what gets delivered on YouTube. So there might be a little latency, but we will get to everything you ask. Okay, fine. So, what is CloudxLab? CloudxLab is an AI-enabled edtech platform for solving the skill gap in emerging technologies. So, by emerging technologies, we choose big data, computer, machine learning, deep learning. So, those are the topics which we focus on. We'll talk a little more about what CloudxLab has and how it can help you in improving your career. So what does CloudxLab want to do? It wants to make learning fun and for life, a continued learning experience. What you would realize is that we are in what is a very dynamic age, which means that we have to keep learning new things. You just can't learn something and then hope to have a complete career or a great career based on that. What you have to be prepared for is a constant process of learning and constant process of updating your skill sets to make yourself relevant for the industry.
Learning new things.
So we do is at CloudxLab, we provide videos, we provide quizzes, hands-ons, projects, and case studies to give you a complete experience, a hands-on experience of learning. So it's not only videos. We have we'll go through some of our projects. Actually, what the Yolov4 I'll do today is actually one of the projects we have on CloudxLab. So yes, they are all very real life use cases. So what's CloudxLab? CloudxLab is a playground. It's got a hands-on. This is what the hands-on platform will look like. There will be a bunch of instructions on the left-hand side, and the right-hand side you have what is called a console for console, a Jupyter console, where you can type in code. So you can type in code, and you can submit your answer, and if it's correct, you will be told that yes, you have a correct answer. And in case you have questions or doubts, we have help sections that are there. The whole process is gamified to keep it interesting. So what is CloudxLab? As I said, again, it's an online cloud lab that comes with pre-installed tools and software, which covers topics of AI, machine learning, deep learning, data sciences, and big data technologies. So what you get is you'll get a platform. When you start, you will get a platform directly from which you can start working. You don't have to spend time on installing tools or getting an environment to work for. Okay, so you can just get started immediately. That is really nice about it. So that's the kind of platform you would get if you work in a big company. You wouldn't really have to spend time on making installations, etc. So this is something. And if you're really a starter, you don't want to spend too much time on learning the tool flows and all the installation issues. So all that is taken out, and what you get is a nice little platform on which you can get started immediately. So as I said, with a CloudxLab, we provide real experiences. You don't have to spend too much time with downloading and installations. You have access to some central data sets with which you can get data directly for your learning. The other nice thing, as I said, the whole thing is just browser-based. So you can log in from any device, anywhere. All you need is a functional browser, and you can get started immediately. Okay? Cool. Yeah, we will. Okay, so this is how the assessment platform looks like. You would have something on the left side, and you have the functional thing on the right side. What I'll do is I'll just show it to you. Also, I think I have one of it open. So you have some. I've literally gone to the course. And for example, over here, there is a question says make a directory, and it's asked me to make a directory named XYZ. So I could do mkdir. I think I may have broken it up. So I could have supposed to do this, XYZ, enter. I can submit my answer, and it says I'm correct, and it will just keep going forward, etc. In case you have questions, you can ask for a hint or see the answer. What we also have is a platform where you can talk to a lot of your students. There's a lot of interaction happening, both at the comments section under each slide, and there is also a dedicated forum platform with which you can ask questions. So Overall, what we try to do is we try to simulate a classroom experience, an experience where you can collaborate with fellow learners all across the world. Students, there's a lot of interaction happening both at the comments section under each slide. So again, these are more examples. This is with a Python with a Python interface. So we have again a lot of tools. What we try to do is we try to Python, Linux, SQL, Java, deep learning tools, big data tools. We have what's like a very social platform where you can share what you're learning with your fellow students. A leaderboard that increases engagement and drives motivation. We also have hiring partners. So in case there are jobs that are constantly posted on the platform, which you can apply, and we enable these connections between our students and people with. Okay, so the instructors and authors of today's lecture, so there's Sandeep Giri, who's the founder of CloudxLab. He is also an AI advisor at AlgoWorks. He has several years of experience with Amazon, InMobi, Shaw. Previously, he's been a co-founder of another startup. He is an alumnus of IIT Roorkee. Abhinav Singh is the other co-founder at CloudxLab. He's got a lot of experience with edtech and gaming, and that has contributed a lot towards our offering. So he's worked with Byju's and Hashcube, and has a lot of experience in building products at scale. The guy in the middle is me. I'm giving the class today. So I am Praveen. I am the CTO and co-founder at Yatis, where we do IoT and ML, especially at the edge. I've worked in multiple semiconductor companies before this. I have a few patents and conference papers to my credit. And I graduated from IIT Bombay with 2 degrees in electrical engineering way back. Okay, so now we're coming to the topic. So computer vision is right now everywhere. The smallest of places, you're seeing a proliferation of cameras all across the world. And people are trying to do computer vision at all spots. And computer vision is definitely improving our lives. You can see it from medicine, from traffic management, robots, everywhere you're seeing. So computer vision is impacting a lot of science, a lot of different subjects. It gets impacted by mathematics, computer sciences, etc. But it's getting used in a lot more places also, and is impacting biology, physics, engineering. Everything is getting impacted by what's being learned in computer vision. Okay, now let's talk about what is machine learning first. So machine learning was called a field of study that gives computers the ability to learn without being explicitly programmed. So this is a definition that came way back in 1959 by a guy called Arthur Samuel. So what is machine learning? So we will have a fun experiment to show you an experiment of what is machine learning. So probably a lot of you guys have played Mario. So in Mario, what you have is you have Mario, fat Italian plumber, who is on a quest in this kingdom that has turtles, and then his aim in the end is to rescue a Princess Peach, and at the same time he has to tackle these crabs and turtles that could potentially kill them. So the guy over here is Tom Murphy the seventh. So he wrote a paper. He demonstrated that he demonstrated a tool with which that could learn to play to play a game. And at the same time, he has to tackle these crabs and turtles that could. Second, give me a second. Okay, there seems to be some error over here. What's wrong here? Yeah, so this is it's a YouTube link, and all of you could see this. And so what this is actually this is how this is a computer learning to play Mario. So first day, what you saw, he was doing some random things and really could not succeed in playing. Now in a few days, he actually gets better. He's able to go forward. He looks forward a few frames. He's learned what to do. Now he's kind of stuck at this pipe, and he's trying to tackle these pipes. Not great. A few more weeks of trying different items, Mario still gets better, and right, he's kind of playing it pretty well, reasonably well, quite good, quite comfortably. He knows what to do if he sees these crabs. At times he looks stuck, but he does know to save himself. And let's see how far he gets better. So as you see how he's progressing, okay, so looks like he has no problem at all, and Mario can do whatever he wants. So Mario is getting really better. Now Mario is quite an expert. And let's see what he does. So now let's see, Mario actually gets so good that the tools got so good that it's able to exploit bugs. Okay. So you saw this, what it did, it just did something very weird. It took a jump in the middle and it knew how to tackle. So this is almost like a small glitch which the computer identified after a lot of experiments. So it knows that it can exploit these glitches. It's learned glitches, not only play, it's got so good that it's identified glitches. This is another glitch you're going to see. So what did Mario do there? Just jumped. He figured that he could jump there. So these are signs of intelligence that comes in, that's learned. Okay, so suppose you had this program that has learned to play Mario. So now if you've given a new game, what do you think would have to be done? You would think that you would have to write a new set of rules, and write essentially a new program to play something like Pac-Man, or do you think that you could just take the tool, plug it to Pac-Man, let it play this game for a while and learn the rules? What do you think is the right thing to do? Okay. So in the old method, what you would really have to do, you would have to write new rules. But if you're running machine learning techniques, what you could do is you could let that existing program just play Pac-Man, try a few things out, and it would figure out what the best rules of the game are. Okay, that's how it would work. So you really don't have to rewrite rules or rewrite program. The same program can be used. So that's one difference between machine learning and traditional rule-based rule-based implementations. Okay, so now so the other question comes is, what's deep learning? So deep learning was largely inspired by nature. Okay, so by nature. So there's like for example, birds inspired us to fly, and human brains inspired us to get higher levels of intelligence, and that inspired neural networks. Okay, so now how does any machine learn? So now so the other question comes is, what's deep learning? So deep learning was largely inspired. So how the machine works is that you basically have a lot of data and then you have an algorithm. So you feed a lot of data to the algorithm, and the algorithm finally figures a model with which it can model this data very efficiently. Okay, so that's what it tries to do. That's what the entire machine learning progresses. The same thing is done by machine learning or by deep learning. It's the same story. Okay, so in a live, and then after you have trained this model, what you would get is you just get new data, live data, what's called live data, and you would feed that to the model and do a prediction. Now, what we'll do is we'll give a slightly simple example to say how that really happens. Okay. Now let's talk about something simple like predicting salary. So you have to predict salary based on number of years of experience. Okay, now how would you do that? So to begin with, you would be given certain salary figures. So for example, you know that after 1 year, the person is getting say 2,000. After 2 years of experience, the person is getting 4,000. And after 3 years of experience, the person is getting 3,000. Our question is so this would be your existing data. And then the question is, okay, if somebody comes with 4 years of experience, how much should we pay them? Any guesses? Any guesses, folks? So it is 8,000. And how would that be? So this is how you would actually formulate the machine learning problem. You would have historical data that you already have, or what we would call pre-labeled data. So you will have, say, years of experience in salary levels. And now looking at this, you can see a real clear pattern, and you would put that into what's called a training cycle, and identify a model that would be able to model this information. Okay. And then what you would do is you would feed in the next piece of data that came in. Okay, what do I pay somebody who's got 4 years of experience? And this model would give you the figure. Okay, it would ultimately give you a figure. So as you can see from this model, in this particular case, it's very simple. It seems that the salary is actually just a multiplier. You just have to multiply by 2,000 rupees, 2,000, and you get a particular salary level. Okay. So now how would a computer do it? Computer would just put in data. Okay, on the Y, you got salary. On the X, you've got years. And you just plot it. And in this particular case, it's a nice straight line. It says, hey, I can model this very easily. It's just one straight line to do this. And you give me any number of years, I can just put it on the straight line, and I can give you an estimate of the salary the person should get. Very simple. But in real life, the truth is that life isn't perfect, and you never get what's a straight line. What you have is data that's slightly off. Right? It's always slightly off. It's never perfectly right. So what you would do is you would do what's called a best fit for it. And that's what the model would do. It would find some sort of relationship that gives the best estimate, that would do the best to put it together. So there would be this line that kind of has what's the least error in all of them. Okay. And the method the way this is done is called gradient descent. Okay, so gradient descent is a little greedy. So the way it starts, it makes an initial estimate. And what it does with an initial estimate, it says, hey, what are the errors? What are the errors to the actual numbers? And once it's figured what are the errors, it would change the slope, say change one of the parameters, say for example, the slope a little bit, and see what happens. Okay, and it would see, okay, if I change the slope slightly in this direction, it says, hey, is the error increasing or is the error decreasing? And if it says, hey, the error is actually decreasing when I take the slope in this direction, it would give you a next estimate of where you take the slope more in this direction, and that's closer. So it would now have a next estimate. Okay, so what happens is that this change in the slope is essentially proportional to the decrease in the error. So if the error is decreasing really fast, it would say go more in that direction. That is the right direction. In reality, what we have is we have something called a learning rate, like a constant that is multiplied. And you basically can calculate the old slope and have a small delta based on the errors you have seen over here. Okay, that is how this thing is working. Now, what if it wasn't the other way around? What if because you've changed the direction which you've gone, the error has decreased? What really happens? Basically, what happens is it just goes in the opposite direction. If it says if the error is if by increasing the slope the error is increasing, then it says, okay, what I really need to do is I need to decrease the slope. So that's how gradient descent works. It's an iterative process. It gives an estimate and looks at what impact that estimate has had on the overall error, and it keeps iterating after that. So how does gradient descent work? If you want to put that into a flow chart, how would it look? So you would start with a random line, and you would say increase the slope a little bit and calculate the change in error. then you would say, hey, did the error decrease? If the error has decreased, then hey, increase slope. Okay, error decreased every time I increase slope, so let us just keep increasing slope. But instead, if the slope is the error is increasing, let us decrease slope. That is how this works. And if error didn't change, then it says, hey, yeah, this is your best fit. Live with it. This is the best thing you have. You can't go further than this. And this keeps on going. This cycle is called an epoch. It's one cycle where you go make an estimate, change one of the parameters like slope, and you feed that back. That is that entire process, that entire iteration is called an epoch. Okay. In case of questions, please let me know. A second. Okay, so I'm going to give another example of gradient descent. Give me a second. Okay. Fine. So I'll give you another example of gradient descent with a real life analogy of a tap. So let's assume that you've gone to a hotel and you've just walked to the bathroom and you want to use the shower. So you have a certain estimate of how much. Second, let me just get back on the. I'm just going to see if there's any questions. Okay, so I'm going to give an example of this. So how you would start? You would go in and you would start with an initial estimate. Say that could be the middle, and you would see, hey, does this water comfortable? And if it's not comfortable for you, you would move that in a particular direction, a small move in one particular direction, and then you would check if that change is taking the water to a temperature level that you're comfortable with. Now, if you're comfortable with that, you would move further in that direction and come to a new position. And then you would again start checking, hey, is this the right spot or not, over and over again. So that's like an epoch. On the other hand, if you first went to, say, the anti-clockwise direction and you figured, hey, this is actually taking me to a more uncomfortable position, what you would do is you would move in the opposite direction. Okay, so that's how this would work, and eventually you would find what's a comfortable position, and that would be the way you work. Okay, so that is one way. Give me a second. Any questions? Okay, I'm just trying to get back the link for the YouTube. A second. Okay. So now let's give an example. Let's make it a little more complicated. So you've gone somewhere and now you have two of these taps, so one for hot water and one for cold water. What would you do? Then you would basically be playing with two pipes, two taps. You would have what is two knobs to play with. Okay, so you would have hot water, one knob for setting a certain level of hot water, and second knob for setting a level of cold water. And you would basically play with these two knobs till you get a particular flow and a temperature that you're really comfortable with. And the way you do it, you keep moving again, taking one step in a particular direction. And if you find it's too much, then you go in the opposite direction. On the other hand, if you see that it's going in the right direction, you would keep moving going forward. Okay. And in reality, what you would have is you just have many more of these input features. So for example, you're trying to study this data across multiple people, you might find out that are certain in the impact of a person's background, the person's gender, the person's age, the climate, the particular climate of that particular point, etc. All contribute to a particular what a good flow and temperature would be. Okay, so now let's talk about what is deep learning. And so a lot of people have questions, what is deep learning? So what we have, what's neural networks? Neural networks is essentially architecture where uh, you've got points like these. Okay, so you have, these are not really circuits, but these are actually programs that are generated. So you've got input data coming
And
at
so,
these points, and you have output data coming in here. And what you have is you have something, one layer in the middle that is basically connected to all the layers previously and all the output layers in the front. And what's happening is that that is input coming in from all sides, and they have different weights, and these weights are then get put together and they get processed at these intermediate nodes. Okay, and this keeps happening, and this is a neural network. And if you have, so in this neural network, you have this layer is called the input layer, this layer is called the output layer, and this layer is called the hidden layer. Now, this is, so if you just have one single hidden layer, that's called a simple neural network. If you have more than one hidden layer, like for example, to model something much more complicated, you would have you would what and you would call this a deep neural network, and this is deep learning. Okay, this is deep learning. So what is deep learning? Deep learning is basically neural networks that have more than one hidden layers. Those are called deep neural networks. Okay, just give me a second. So yeah, as I said, these are the output layers. Okay, so now let's talk about a first example of computer vision. So one of the biggest data sets in computer vision is this data set called MNIST. So what is M? So MNIST was this data set where you had lots of handwritten numbers. So numbers from 0 to 9, sorry, now digits, collected from lots of students essentially, and they basically, a lot of students have written it in different ways. Each of these, so this data set basically had 28 by 28 pixels. They were all squares, and all of them had basically handwritten digits, and this was simple black and white. This was one of the first problems which people tried to solve with computer vision for the longest period of time. And so trying to put that into the deep learning perspective, what you would have is what they did is they essentially just first flattened this neural network, this image. So what you had was you had an image of 28 by 28 pixels, and so 28 by 28 is 784. So what you had was 784 inputs per image, and that would be put into this neural network where each of these layers are connected to all the pixels, and they're all connected with different set of values, and those values are called weights. Okay, so these are called weights, and what you would have is you have labels on this side. So you have labels from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 10 digits, and you would have 10 possible outputs for every picture. That's how it works. Okay, so what you want is basically you want this neural network to output a set of probabilities. So what you want is I'm going to feed in these pixels from this side, and on this side, what I will get is a bunch of probabilities saying that, hey, what's the probability of this being a zero? What's probability of being a 1, probability of being a 2, and so on. And what you would want at the end is that you would want that the probability of 8 in this case, the correct number, would be the highest. And if you have trained your neural network in a correct way, it would tell you that, hey, this neural network, this output that corresponds to the number 8 has the highest probability, and therefore that is the correct answer. That is what you would want eventually. Okay, so now how does this happen? How do you get these probabilities from this neural network? Okay, so now what happens is that initially what you would have is you would need to get what's called good data, good labeled data. So you would take a data set where you're given these pictures and you're told that these are the actual numbers associated with these pictures. So it would be 0, 1, 2, 3, 4. So for every picture, you would have a particular label associated with it. Okay, and this is like good data. So this is the good one. Okay, so for example, in this case, if you have 8, you would see that what would it be? The actual would be, there would be all zeros, and there would be a 1 at the point corresponding to the 8. That is how. So you basically get a 0 or a 1, and that's it. So you would have a 1 corresponding to the point where 8 comes in. Okay, and so now you take an instance from the training data, and you would put it through this network. So what would happen is that all the pixels are fed in, they get multiplied by certain numbers, and certain intermediate values are calculated. And then that goes through the next layer. Okay, so this process of moving your input data across the neural network is what's called a forward pass. A forward pass. This is a forward pass. So as you go through, as you push it forward, you get a forward pass, and you finally get a bunch of outputs. So you will have some actual computations. So in this particular case, yeah, your first set would typically be wrong. So it would have actually predicted that the 5 is actually correct one. Then what is done is that what is computed is checked against the actuals. And what you get is you calculate the error. So as you can see in this case, the error is really high because the first pass actually showed that 5 is correct and not 8. Actually, 8 had a very low probability. So what is done is that this information is then fed by, is kind of incorporated. How is it incorporated? You freeze every layer and you basically check what is the impact of this first layer on it. This is done by a bunch of checking what's called differentiations. And you would find that for every layer, you would go find differentiation, and you'd find what is the impact of the weights at each of these points. And you would figure in which direction. So like we did slope, you would try to see which direction you want to move your slope to get correct. Okay, then you would take your next instance and you would keep doing this over and over again. And this would be one iteration or one epoch. Okay. Now that's how you would do computer vision with deep neural networks. So let me just check in case there are any questions. I'm just going to jump in. Okay, just let me know in case there are questions. I'll keep checking them over here. Okay, so going back. Okay, so now that sounded good, right? What is the problem? Why can't we just scale that up? So in a simple picture, in a really simple picture, so the last pictures we was just actually 28 by 28 pixels. That's very small. The simplest pictures we work would have 100 by 100. So the number of, and if you just had 3 layers, you basically would end up, so if you had to make a fully connected neural network, right, which the traditional neural network where we showed, where each layer is connected to the previous layer and to the layer proceeding and preceding it on both the sides, you basically have an enormous amount of connections, an enormous amount of weights, and enormous amount of numbers that you have to calculate. So the total number of connections actually for this, if you calculate, is about 200 million for something as small as doing 100 by 100 picture. That doesn't work. Okay, so one of the points is that in these images you got to notice is that, say, a pixel over here really doesn't have much relationship with the pixel over here, and you don't really need to connect this pixel and this pixel together. What you're really interested are pixels that are just close to each other. And so CNNs basically came in. These are convolutional neural networks, and these came in to solve the problem, and they did a much better job. Okay, so I'm just going to do so this vision, so whole the concept of perception among is a very difficult problem. So humans do it very, very well, and computers do it very, very badly. Okay, so the oldest ways of machine learning was you could say was an advanced level of statistics, and machines very quickly became much better than humans at those tasks. They became much better than humans at those tasks. Back in 1996, machines started beating humans at chess, but the machines at 1996 couldn't really do any computer vision decently. So if you were given a picture of a cat, a baby could say that's a cat or not a cat, or you don't need somebody with very high IQ to say that. But for some reason, a machine that could beat Garry Kasparov at chess could not do this easily. Okay, so there's this interesting paradox which Moravec said, that is that so reasoning skills, which are considered high level skills for humans, they require very little computation. So when you're trying to get a computer to do it, it's quite easy to do that.
IQ to say that.
But
For some reason, a machine that could beat Garry Kasparov at chess could not do this easily. Okay, so there's this interesting paradox which Moravec said, that
among humans,
is that very
like even babies can do it at a very
reasoning
early
skills,
age.
which are
But to
considered
get a
high
computer to do
level
that, it's
skills for
very,
humans,
very difficult.
they require very
So that was
little
something
computation.
unique,
So when
which
you're
people
trying
were
to
trying
get
to
a
figure
computer
out.
to do it, it's quite you don't need easy somebody to with very high IQ to say that.
But
For some reason, a machine that could beat Garry.
It's during these studies that this idea, with people trying to study how the brains worked, that this idea of convolution neural networks came up. And a lot of it came from the study of the brain's visual cortex. And so the brain's visual cortex is on the back side of the brain. It's on this side. So this is the front side, and this is the back side. So that's where most of the component that helps you see is. So let's look at the architecture. So this is like the whole brain. So visual cortex is somewhere in the middle over here, and there are certain sensory the motor, the part that actually controls motors, that helps you move, your hand as I speak, and I'm moving my hand, that part. And if I want to go, say, move my mouse to this point, what is being activated is the primary visual cortex is taking feed from my eyes, and just creating some information. And finally, some components over here in the motor cortex is sending signals to my hand to say that, hey, this is where, move the mouse in a particular way to highlight this. That's what's happening here. And I can do it quite easily, but getting a computer to do the same thing, it's really a lot of work. This is just a much deeper look at it. Well, basically what you have is a primary visual cortex that first gets the feed of data, and then you have a visual association cortex, which is, you could see, is just like more layers within.
This is where move the mouse in a particular way.
So it's like the data has come in here, and it gets processed by multiple layers of brain cells or neurons, and they get processed into information that can be accessed better and better. Okay. So now, back in 1958, so among the first guys who were trying to study, so people who were trying to understand the brain works, so they made a couple of experiments on cats and monkeys that kind of gave ideas of how the brain is really done, and gave some syntax to this. Okay, so what they did is that they created an experiment. They took a cat and they surgically embedded electrodes in certain parts of the brain. Actually, so in this particular case, the visual cortex, and they adjusted the electrodes in such a way that they could, say, tap a particular neuron. So they could tap a particular neuron, and what they did is that they showed the cat a light bar, and they moved it, and they connected this particular electrode to a microphone. Sorry, not microphone, a speaker. So what they essentially got is they started listening to what is happening in the brain. Okay, so I'm going to show that. This is again a YouTube video. Yeah, so there's something wrong with videos being unable to play. I think I'll have to run this on YouTube. Give me a second. I'm going to run this on YouTube. So what is this? So this the tick 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 you're hearing is actually the sound noise from the electrodes. And so what they did is that they showed the cat this electrode that is they've tapped, and they gave this cat this particular they're showing the cat this particular line, and what they're finding as the line is in this particular region, that particular electrode is getting highlighted. So whenever the light is coming in this region that's marked by these X-rays, the electrode is getting, so that particular nerve is getting activated at that point. As you get further away, then that particular item is not getting classified. So they could make it bigger in a different direction, but that particular item doesn't get doesn't get activated. So the region around, so the one near the X, the activation seems to the highest. As you go further away, the activation gets lower. That's what they found, and they did more experiments, as you would see. So they said, okay, somewhere close by, so where they put the X, the activation is highest, and somewhere around that, the activation is slightly lower. And as you go further away, there is no activation. If you change the direction, so it's again, if you're going to the same area in a different direction, different orientation, there isn't much activation of that particular neuron. So that's what they found. But in this one, yes, it's working. In the others, it's not. Okay. So what does this mean? I'm just going to go back now. I'm going to stop that video. So what does that mean? It means that there were neural layers. There were neural layers that had a very small, that were focused for certain patterns, for in certain regions. Okay, so there were special parts. So some parts of neural network they could catch. So this particular neuron which they had caught could basically catch a 45-degree angle in a particular layer in the image, in the site of the cat. And so what they figured it out, there are these lot of these layers that basically first catch these simple edges of different orientations and different sizes and different pictures. That's what it does. So the first layer is something very simple that captures these simple edges with very simple shapes. So that was the idea of a convolution neural layer. So what they said is that these neural networks that we're going to create, we're not going to just connect everything together to everything. What we're going to do is we're going to specify a certain area, I'll call a receptacle field, and only the layers. So for example, over here, okay, so we're going to say if this is the area of interest, so this neuron over here is connected only to this layer, only to the pixels in this layer. And this neuron over here is connected to pixels in this layer. So this is how they started creating convolutional neural layers. So this is called a receptive field. So they define a receptive field. And now the relationship between these different layers are not connect everything to everything, but instead connect only the pixels in that particular receptive layer to the to the preceding layer, to the next layer. Not all of them, just few of them. And you keep building that. You keep hierarchically building that. That is how they started building neural networks. Okay. So as I said, yes, so each neuron is just connected to the second convolutional layer, only to neurons that are located in that small rectangle, this particular rectangle, which we've called a receptive field in the first layer. And you keep doing this over and over and over again. So what this means is that the first layers, what would do is would concentrate on extremely low level features, like we saw in the cat example. That's what's really happening in the human brain. It just captures extremely low features that would mean a simple edge, a simple line, and nothing more than that. And then what would happen is that as you go higher into more and more higher convolution layers, they would start getting assembled into higher level features. Okay, that happens as it goes through and through. And so it turned out that this hierarchical structure is very common for all, is very good to model real world images, and is in some way what's really happening in our brain. So you don't have to do something as complicated as this. What you need is something like this. So you don't need to do like take all the pixels in the previous layer, connect all of it together. You totally don't need to do that. What you need to do is you need to identify a particular set of pixels and just connect that in the next layer. And that's how a convolutional neural network is made. Okay. So here, as we said, this is an input layer, and this is called a convolution layer. This particular rectangle that we define is called a receptive field. And this is how you basically have one layer. What you have is this, and this relationship of, well, basically what happens is that the pixels over here get multiplied by certain numbers. And those numbers that get multiplied are called filters. So you'd have a filter like this or a filter like this. So you'd have multiple filters that get used. So for example, this particular, if you have a filter that looks like this, what it's doing is catching horizontal vertical edges. So it's just identifying vertical edges. And a filter like this would catch horizontal edges. And what you would have is you have several of these filters running over and over again, several and several times, eventually building more and more context in an image. And finally, this is how a computer is able to see. Okay, so this is an example. So there's another set of layers, another set of example of a convolution layer is called a pooling layer. So what a pooling layer would do is that you would again divide a receptive field, and it would only pick up the value of the highest pixel. So you do that finally trying to shrink images or trying to summarize it. So what is done is that so how computers really see today,
so what a pooling layer would do is that you would again divide a receptive field, and it would only pick up the highest the value of the highest pixel.
Convolution layers and pooling layers, and at the end they have these classically fully connected layers. So this is like a typical convolutional neural network. And if you and all of these, there are a lot of values, weights, etc., that are at different points at inside these filters and inside these pooling layers. And once you get the right kind of numbers over here, you have a model that can identify what's seen in a picture. So this is how computers see. Okay, so has this been working? Well, it's been working quite well. In case any questions, let me just check. Okay, there are some conversations over here. Fine, let me just jump up. So yeah, so there's one great competition that's happened. It's called IMAGENET. So IMAGENET was this competition that ran online from, I think, from 2010 to 2017. And what it was basically, it had about 1.4 million images, and they had 1,000 object classes and quite vague object classes. And the challenge was, can you create a model that can identify this really fast? So what happened is, so this is again, as I said, from 2010, and it ran all the way to 2017. And it's estimated that for that similar data set, a human would have an accuracy about, well, this is an accuracy, this is an error percentage, would have an error percentage of 5.1%. And so when they started around 2010, the best models had about 28% error rates, which is really bad. That basically means about 1 in 3 of every prediction would be wrong. Well, it's about 30% incorrect. And as we went down, somewhere in 2015, the models were able to beat humans. Okay, models were able to beat humans at this particular point. And so it's what I'm not trying to say is that all computers can see better than humans at all points. It's not, but it's really becoming difficult. So there are so if you're trying to get, so if you've been doing those, probably every time you try to log in, you're seeing very difficult challenges that have been thrown to you to show that you're not a robo. And the reason why they're becoming more and more difficult is because computers are able to see a lot better. So hackers who are trying to hack are able to create tools that can read a lot of those easy passcodes. And so right now people do extremely complicated things to make sure that only humans are able to to evaluate that image to filter robots. And one of the reasons it's happening is it's over here. So for a lot of standard tests, computers are way better than humans. And for something especially that's repetitive and you have like a defined image set, computers can be trained to beat humans for that. Okay. So now problems related to image classification. So I'm going to talk about a few problems related to image classification. Some are called object detection, action classification, image captioning. These are some problems that are related to image classification or computer vision. So this is typically a typical CNN. So what you would do is you would pass it through, and this is a classification task. You would basically pass it through, and you would get a bunch of outputs. So, for example, in this particular case, the cat has the highest probability, and as you see, is this image has a cat. So that's what you'd want. So now, what are different types of computer vision tasks? So one of the tasks is basically was which you saw before was classification. Does this have a cat or not? The other point is about now this concept of semantic segmentation, where you're just trying to identify the pixels of different items separately. That's what's done over here. That's called semantic segmentation. The other item, what you would do over here is what called classification and localization, where you see there's a cat and you would put a box around the cat. Then the next kind of problems you'll be talking about is object detection, where you would not have one, but you would actually have multiple items to identify. For example, you would have, in this particular case, you said there are 2 dogs and there's 1 cat, and you want to identify them and you want bounding boxes that capture both of them. So this is among the most interesting problems, and this is what we would we would use Yolov4 at the end of the day to implement or to show how this works. An instance segmentation in which you basically identify each item and then you kind of identify the pixels that belong to the dog for this dog, this, and the cat, all separately together. And that particular act is called instance segmentation. Okay, now how does computer vision, how does classically it work? So one of the, so how do you go from classification to object detection? So what they did was that one of the ways they said, hey, let's have what they call a sliding window technique. So what they did is, hey, let's have a sliding window and let's detect if the pixel in the center belongs to a cow or a cow or grass, etc. So what they would do is that they would run multiple windows of different heights and width across it, and each of it would get a certain output, a certain classification. And what you would do at the end, you would merge all of it. Now that's extremely slow, painful process. But what YOLO does is that YOLO takes that a little further, does it very elegantly. And what it does is it's got this particular deep CNN, and with one pass, it basically creates a lot of detections. And then what you have is at the end, you have a process in which all of it is merged together and you get a final output. So we will see how that works, okay, as we go forward. Questions, relevant ones.
with one pass, it basically creates a lot of detections. And then what you have is, at the end, you have a process in which all of it is merged together, and you get a final output. So we will see how that works, okay, as we go forward.
Okay, so here I have pooling layer. So what the pooling layer does,
it basically creates.
So you would have, say, so you should see this in context of the entire convolution process. So a pooling layer, what it does is that if you're given an input image and you define a certain receptive field, you would, at the next stage, what you would get is you would either get the maximum value of it or say the average value of it. There are two types of pooling layers. Some pooling layers capture the maximum, and there's some that capture the average of it. So if you have what's called a max pool layer, and you have 1, 5, 3, and 2 in this, these are the values of the pixels, and the next stage what you get is a 5. And this is a nice way of summarizing it, of summarizing data. What it also adds, it adds what we call invariance. It adds certain objects are in different places. This kind of helps you reduces the what's called makes the image variant. It adds location invariance to the image. So if it's somewhere else, or this particular castle was somewhere over here, you would still get, at the end, the convolutional neural network will be able to predict that this item is over here. And one of the reasons it's able to do is it's because of the max pooling layer. Another way of looking at it is that what it's doing is it's kind of summarizing that image into something much more quickly. So that's another way of looking at it. Okay, so as I said again, there are two types of them: a max pool layer or an average pool. Okay, cool. So now we're talking about YOLO. So YOLO was called YOLO because it was, it's inspired by there is nice word that says you only live once. And so they call this you only look once. And because a lot of the previous models, what they did was you always had to run multiple convolutions over multiple, and then and these convolution processes, as you would have understood by now, are very computationally expensive, and they take a lot of time. And so in case you're trying to do something like, say, computer vision in driverless cars, you can't have something that's not fast. You need something that operates at real time. So YOLO was one of the first models that made it possible to have a decent level of accuracy at real time, so on a GPU. So this came back in 2015, and we will talk about. I'll give it a high level of how YOLO works, and there have been multiple variations of YOLO. So right now, the latest one they have come is called YOLO CSP, that came, I think, a month ago, and they're all moving forward. They're getting better and better and better.
Decent level of accuracy at real time on a GPU. So this came back in 2015, and we will talk about. I'll give it a high level of how YOLO works, and there have been multiple variations of YOLO. So right now, the latest one they have come is called YOLO CSP, that came, I think, a month ago, and they're all moving forward. They're getting better and better and better.
Okay, so this is the guy, the team that makes YOLO, and I just wanted to highlight a particular way of looking at it. Okay, so it looks like I'll kind of will try to explain what this is. So this what they were trying to show. They were trying to show multiple models, and they're trying to compare two important parameters of it. One is accuracy, and that is speed. So what they have is they have a value called AP. It's called average precision. It's a metric for accuracy of how good is the quality of prediction on this side. And on this side, what you have is the speed, the time for it would take to process one image. So this is in milliseconds. So as you can see, as you can understand, if you want something more accurate, it might take more time. Okay, so that's the point of it. So what we have here is, so the latest model they have come out is called Yolov4. scaled YOLO CSP that's shown in green, and it's kind of over here. So what they have is they have multiple variations of that of a model, some that are more accurate in that same field. And as of right now, YOLO scaled YOLO V4 is right now, as you can see, it's got a highest level of accuracy for an equivalent amount of speed. So, so another interesting parameter that you have to remember is that a real life image with a decent quality camera, an average camera, produces 30 frames a second. So you want something that, so if you want to really be able to process a real time video from a real feed from somewhere, you would have to be at least on this side. Okay, so over a period of time, so what we have is you have YOLO V3. YOLO, the first one is not even shown. This is, I believe, it's a 2-year-old model or a 3-year-old model that is over here. And over a period of time, they've been pushing it. So as you said, as you can see, they've been pushing up accuracy and they have been trying to improve on speed also at the same time. So sometimes you want, but in case there are certain applications where you really don't care about speed, you can, if for example, you're trying to do a diagnosis of medical image, you really don't have to, it doesn't really have to be real time. So in that case, what you could do is you could use one of the models that are bigger, but are more accurate over here. So the models you see over here are called efficient det. These are models from Google that came earlier last year, very early, yeah, early last year. So this field is really moving very fast. There are new models coming, and the new models are getting better and better and better. So the what we have is YOLO V4. That's the demonstration we have, and you could do some minor. And you could actually, the same framework could be used to run YOLO CSP also. Okay. This is how this looks. Questions? Okay. So that was what YOLO. So I'll now tell you at a very high level how YOLO is working. And as I said, there have been, since 2015, there have been multiple versions of YOLO coming in, and the same, I won't say exactly the same team, but there have been teams working that have been pushing it forward, getting it better and better. So how does it work? Basically, the picture is resized and they run one convolution that creates multiple predictions. And at the end of it, you filter the number of predictions using a concept of NMS, or non-maxima suppression. That is the process that's used. Okay, so now I'm just going to talk. So what happens is, say if you get an image like this, what YOLO does is that it gives you predictions per grid. Okay, so reality, what YOLO does is it splits it into a 19 by 19 or 13 by 13 grid, depending on the model and the accuracy it does. But I'm going to explain how it works by using an example of a 3 by 3 grid. Okay, so if you have an image like this, and as you can see, we'll be detecting people and balls, soccer balls. So what would do is that what YOLO does is that for each box, it would give you an objective score. So like, does this grid have a midpoint of an object? And it would give a bounding box and a confidence of those bounding boxes. Okay, so now, for example, it's for this person, for example, it would say, okay, this guy, it says, okay, it's in this grid, the midpoint is over here, and this would be a bounding box, and it would have a certain confidence score. But as you see, this person is kind of so close, and there would be another prediction that would say, nah, there's a certain probability that this guy's midpoint is in this grid. Okay, so what happens is that you would basically have, but yeah, then exactly, then when I come to this guy, and maybe this guy really doesn't have a problem. There is just one prediction, and it says at this point, and the guy is over here. There's no problem over here. Okay, so what is done is that what we do is that so in case you have multiple predictions for the same person, what's done is that you look at these two boxes. Okay, so for example, these are the ones, and then you want to reduce it. So what you would do is you would take each box and compare with each other, and you will see how much, where are these boxes intersecting. So if they're intersecting a lot on top of each other, you would say, okay, these are practically the same box, and you would basically filter it to one box. Okay, that's what's happening. That's what YOLO does essentially. In a complicated method, it would reduce the number of boxes by looking at if these boxes are overlapping each other by too much, by a certain threshold which is defined. If it's then it would filter them out, else it would keep them. So in this particular case, it would say, it would get, in case it got three predictions, it would say, okay, this guy's right, these two, and you kind of need to move it. Okay, so what we have is we have a nice little hands-on project. So in this way, I can demonstrate how a hands-on project works on CloudxLab. Okay, so let's see how that works. So the link is over here. Okay, and so you can go to CloudxLab. As I said, if you go to Cloud, I'm just going to say, so just show you how it kind of looks. So you open to CloudxLab, you kind of it kind of shows you some of the things that are happening around. Okay, and apparently some person's got jobs, etc. So we're kind of trying to make it a more social platform with which you could interact with your peers. And what you would have is, if you want to look at courses, etc. So this, you could go to this page called Explore Courses. You would get it. I've asked for Yolov4, and I can go there, and I can pull it out. So this is something we just released very recently. So what we do here is we do Yolov4, not inducted, but OpenCV. Now it turns out that now why would I do this in OpenCV? And first, what is OpenCV? OpenCV is this tool set for computer vision. It's called Open Computer Vision. One of the most powerful tools for doing
this is something we just released very recently.
There's a bunch of algorithms in it. A lot of it are.
So what we do here is we do Yolov4, not inducted, but OpenCV. Now it turns out that now why would I do this in OpenCV? And first, what is OpenCV? OpenCV is this tool set for computer vision. It's called Open Computer Vision. One of the most powerful tools for doing this is something we just released very recently. There's a bunch of algorithms in it.
You could actually build on top of this.
A lot of it. So what we do here is we do Yolov4, not inducted.
Predicts things and processes the data. This is the best way to do it. Okay. Okay, so now as I showed you on the right, so I have already done it on this side, but what is happening on this side is that we kind of explains what is happening. So what we said is, again, I think a lot of it we've already covered in our classes. So what is it? What is object detection? It's trying to detect an object along with the coordinates. And as you can see, there are a lot of applications today, especially self-driving car, character recognition, robotics, etc. And what we're talking about is YOLO. And this is, again, so this kind of gives you a history of what YOLO is. So it tells you lies. So what you do is you would mark it complete and go forward, because this is talk. And then on this side, what we have is we have a bunch of instructions of how to implement it. And you could follow that. And like, for example, we've got some helper code, and it tells do this, etc. So I have done that on this side. So what I've done is I've imported the libraries they've asked, etc., and created this function. So this particular function helps us see these images, in this platform. And after, so I've run it, and I can submit my answer. And you say it's correct. Then I move to the next point. So what I first did is I imported the libraries. And please note, so this all of you can, you would have to have a lab subscription to do the part on the right side, but the lab subscription is free for the first 7 days. So go ahead, and in case you're not members of CloudxLab, please go sign up and get access to the first 7 days, and you can take that. Okay, so next what we're going to do is we are going to say declare what's called a labels name. So what is a label's name? A label's name is basically what are the items that are available in this particular model. Okay, so in this particular case, as I said, so we have already provided that particular name, the set of names in a file in our data set. And we have, so as I said, we have it over here. If you run it, as you can see, we have got about 80 classes. So this is the pre-trained model that's available by default
So
from
we
Yolov.
have
And so
already provided that particular.
And if you want to check about a few of them, as you can see, the first 5 of them, they got persons, bicycle, cars, motorbikes, aeroplanes, etc. If you want to see all of them, that's also possible. You can say, show me. Well, I think this should work. So you can see all of them also if you want. So these are the items that are available by default. Okay, so I'll just go back to what it asked me to do. C5, I'm going to submit my answer. And I'm going to move forward again. So this way you can kind of play a lot of things and do it. Okay, so now what we have done is, as I said, we have, there were some questions if it's free. As I said, the content on the left side is free. The content on the right side, the lab, is free for the first 7 days. You would have to subscribe to it. So you can sign up for the first time and you'll get 7 days. It's a free period on which you can try the lab out. The content on the instructions on the left side are free. And we're right now running a free offer for almost all our courses, at least all our self-paced courses. So you can take use of that. So the course is free right now. It's till the end of the month. The lab is free for the first 7 days. And if you want to use this lab more and more, you just have to pay for it on a monthly basis as a subscription. And it's not much. You can take a look at it. It might change based on the time and because we keep running offers. So take a look at it. What the current one is. It's pretty cheap, not much. Okay, so now we come to the part where we actually build a model. Okay, where we actually build a model. So the process of building a model is in which you basically have 2 items. You would basically have a config file which defines the connections. Okay, defines what is connected to what. And what you would have is a weights file, which would be the weights of the connections, basically. Okay, that's how what it is. And these 2 items put together is your model. These models are available online. We have just made it available for you easily. Okay, and now what we're going to do is we're going to read the model and build it. And for doing that, we're going to use this OpenCV's a particular. So CV2 over here is basically powerful. From all the experiments I've done, I found out that I've seen that it's actually very, very fast.
And for doing that, we're going to use this OpenCV's a particular. So CV2 over here is basically
platforms we have evaluated for YOLO specifically. This is definitely the fastest. At least on a computer. Okay, and so when I did this, when I read it, I have now created the model. The model is now ready for me to use. Then what we're going to do is we're going to read. We can we'll take a peek into the model, and what we can do is we can get all the layer names. So for this, and if you kind of look through this, you see that there are a lot of these convolution neural networks, and there are a lot of different layers that go into building a very modern convolution neural network. So this model has got 379 layers in it. 379 layers. That's how deep this model is. So this particular, let me just give you an idea. So this particular weights file is about 245
So for this,
megabytes.
and if you kind of look through this, you see that there are a lot of these convolutional neural networks,
there are just so
and there are a lot of different layers that go into building
to run this. Okay, and these are the types of multiple types of convolution layers and other items which is discussed more in some of our courses. It discusses what these BNs are basically batch normalization layers. Then we have different activation layers. There are leaky layers, and these guys have something called a MNIST layer. A pretty very like this is like among the most advanced neural networks we're seeing right now. And what we're interested is we are finally interested in only the output layers. Okay, the output of this convolutional neural network, because that is what we're going to take and that is what we're going to process. So we're going to just identify the output layers. So these are the output layers, and we're going to print out, okay, these are the layers which are finally the output layers of this neural network, and we're going to just tap into that in the end. Okay, our next thing we're going to do is now we're going to read our image. Again, we are going to use OpenCV's tools to read our image. I think I've done this. Let me finish this section. We finish our model building section. Now we're coming to a section where we're going to read our model. So what we're going to do is we are now going to use OpenCV to read our image. And please note, so we're going to read our image in. Are also going to do resizing. So YOLO basically works on 608 by 608 images. So as you can see, the size of this X and Y over here are about 608 pixels on both the directions. Okay. And this is
our model. So what we're going to do is we are now going to use OpenCV to read our image. And please note, so we're going to read our image in.
And if the whole as you can see, there
are also going to do resizing. So if you go to pictures, YOLO basically works on 608 by 608 images.
So you got height, width,
as you can
and
see,
channels.
the size of this
and these channels
X and Y over here are about 608 pixels on both the directions. Okay,
for each
and this point model. So what we're going to do is we are now going to use OpenCV.
And what we're going to do, so this is what an entire picture is. So one of the next steps is basically what you have to create a blob. So this is a particular data structure that is required by YOLO, which is used to process. It's basically nothing. It's very similar like a picture. It's basically a batch of picture in which they change, just the configurations change a bit for the tool to be able to process it. And if you can actually take this particular picture and split it up into its individual color constituents. So what I've done is I have actually taken the picture and split it up into RGB. So basically, so 0 over here basically corresponds to R. The 1 over here corresponds to G, and the 2 over here corresponds to B. So I have taken this and I've printed all of them together. So as you can, so now what does that mean? So this is the red picture. So wherever you see a white, it's either a white, it's where the pixels that have value R have the highest value. So for example, if you look at this particular road or the pavement on this side, it's reddish. And what you see over here, that is white in this picture. So basically it's got a lot of red pixels, but very few green or blue ones. So as you see, it's almost white here and very dark in these two pictures. Okay, so what I'm showing you is that we still have the picture, and you can look at it in all three channels or all three different color streams, and that's how it's taken. And what we
and very dark in these two pictures. Okay, so what I'm showing you is that we still have the picture, and you can look at it in all three channels.
So it's in a pass. So what I've done is this is called a forward pass. As we discussed, forward pass. So you've taken the image, the input layer, and we have passed to the entire.
And very dark in these two pictures.
And it took approximately 1.5 seconds for us to pass this image. So what we right now have on the lab is we don't have a GPU. we have a normal CPU, so it's about it takes about 1 second. On the GPU, the value of this would be around 20 milliseconds or so. It's so much faster than GPU. That's what GPU activation can do for you. Okay, so what we have now done is we've done this layer, which is called processing the input. The value of this would be around 20 milliseconds or so. That we have also done this layer where we're doing a forward pass for inference. Okay, so what we have now done is we've done this layer, which is called processing the input. So what we now have is we actually, so what Yolo has given is basically Yolo has given us a lot of these outputs. So it's created a lot of outputs. And what we need to do is we'll first get all the outputs. So what this does is that it will go across all the outputs. And so what we have is basically we have 3 output layers. As we'd seen before, there were 3 output layers, and each of the output layers has given us several number of predictions. And what we did is we're going to iterate through all of them, and we're going to identify the ones, the boxes that have a higher probability than say 30%, and we're just going to identify that. So that's what we have done. What we're doing over here is basically we just iterate through all the outputs, and we are checking, and what we're looking for is we're looking for the confidences, which is the probability that those boxes contain something real. And we are also accumulating the box coordinates. So that's what we're doing. We calculate the boxes. The boxes are the boxes. Confidences are the values. Classes are the kind of items that have been detected. Okay, so we're going there, and we that those so I printed out different things. So as you kind of and we are also calculating, we are also accumulating here. So this is like going to the first output layer, box coordinates, and what it's got, it's got multiple predictions for balls, as you can see. We saw only one ball, but we're seeing multiple predictions for values, multiple predictions for persons. How many predictions did we get total? We got 24 predictions. So when you did a pass, we got 24 predictions which are greater than our specified threshold, which is a lot, right? So the next step, the next step what we do is now we are going to be only one ball, non-maximum separation. So again, multiple predictions. OpenCV gives us a nice little tool that does this. We get total. We got 24 predictions. So when you did a pass, we got 24 predictions which are greater than our specified threshold, check if those boxes, which is a lot, right? So the boxes are intersecting. The next step each other by as large amount as they are, I'm going to merge them. So after merging them, we end up with just 3 predictions. So there are just 3 predictions left. Now the final tool is what it does is that it basically checks each of these final predictions, and it takes up those boxes, and it uses OpenCV to put it together. And at the end of the day, what we have is a full prediction with just 2 people and the ball. We end up with just 3 predictions. This is how this works. This is how OpenCV, this is how you do computer vision object detection with Yolov4, with OpenCV, Python, etc. Okay, cool. So so a lot of the model files, etc. are already referred on this page. And like in case you want to use, so I've used Yolov4. You do computer vision, you can object detection with download the Yolo CSV models with and Yolov models, etc. And also like use the same code. You just have to choose a different configuration file and the different weight file. So a lot of the and you can run a different model are already referred on this page.
And like in case you want to use, so I've used Yolov4 for
you
do computer vision,
you can
object detection
which you're free to take,
Yolov4.
and you can see how that we also discussed how you can do training on a custom data set
and the different files.
So where was it coming? Yeah, so over here, for example, yeah, the weights file, config file, there's a different weights in a config file for different.
And like in case you want to use, so I've used Yolov4 to do computer vision,
the same code. Also. So that kind of brings me towards the end of today's.
Hello. I hope the session was really useful to all, and we are really sorry for the trouble. I mean, due to some voice issues, it happened. So these are the new course which we have launched. Okay, with IIT Roorkee. Do check it out, and I hope everyone has filled up the feedback form. Thank you.